video from Zimmer and Peacock about quality control in electrochemical biosensor development and manufacturing. Now at ZP, we're what's called an ISO 13485 contract developer and contract manufacturer of electrochemical biosensors. So when I talk about biosensors, I'm really going to be talking sort of in general, but often actually thinking about the sort of archetypal biosensor, which would be the glucose strip. But one of the first things that happens, obviously, in the workflow when manufacturing a biosensor is the IQC, the incoming quality control. So I'll sort of essentially jump over that fairly quickly because we have our incoming quality control. We have our manufacturing where we have our quality control, which could be a nearline, online, inline, and I will discuss these things. We have our OQC, outgoing quality control, and at ZP we control, or we look after much of our data in a system called Julie. Julie is a proprietary database that's online, and people can open up accounts and start subscriptions with Julie. So Julie is a way of us controlling our manufacturing and bringing together a lot of our development data and manufacturing data. And I put a little link to that just there. And then eventually, obviously, we sort of yield, how much do we actually get out of the production, and we package it and we ship it. So this is a general workflow for manufacturing a biosensor. If I was to sort of make it look more like a sort of traditional glucose strip, then you have a sort of something that's screen printed, which may be done outside of your factory, at which point you have to do an IQC, an incoming quality control on it, or if you do it within your own factory, then that's a quality control step to make sure that that kind of screen printing is reproducible within spec, etc. Now that quality control, there could be sort of analytical methods. I'm not going to suggest anyone does a lot of SEM, which is scanning electron microscopy, but that would be something that people would do in a more academic setting. I will touch upon profilorimetry, for example, but there's also more sort of testing. Testing could be like continuity testing. Is my print continuous, or there cracks, etc. in it? So I'll talk about testing, and I'll also talk about electrochemical testing. Now, at ZP, electrochemical testing and electrochemical functional testing is something that we do at scale, which is, I think, very different from other contract developers and other contract manufacturers. And what's nice is because we have this proprietary system called Julie, and as I say, Julie can be used by other companies through subscription, and we can really crunch our data, and we actually can produce certificates essentially for batch release to sort of demonstrate that the work was done. We put all the data into Julie, and then Julie will produce a report, and that report could be signed, and that can be part of the quality system. Now, as part of this as well, there's a sort of next step, which is having made some sort of electrode system, either by screen printing or sputtering, for example. You may want to functionalize it. So in the case of a glucose strip, that could be GDH-FAD, but I wouldn't limit the conversation just to glucose. But in the glucose space, there would be an enzyme would go down there. The mediator would go down there. The mediator is often something like ferricyanide. And then there's all these kind of excipients to kind of look after the enzyme, sugars and things like trehalose and buffers and salts. Now there's a sort of, as you do this kind of functionalization, you could do quality control. And again, at ZP, we're fairly unusual that actually our quality control is sort of functional testing. So we can sacrifice some of the products and actually just test them at a low analyte concentration, at a medium analyte concentration, and at a high analyte concentration. And again, we can put all that data straight into Julie, automate the production of a report or certificate, and sort of move the product along the traveler form, and get these certificates as we go along. The sort of final step then is maybe to put these, to sort of laminate it and put a sort of what's called a capillary over the top of the sensor, something that will sort of bring the sample to the sensor, and something that will hold the sample essentially in place. In the case of a blood glucose strip, that would be blood that would be sort of capillary filled there, at which point we can do an OQC on this, which you could describe as being similar to that QC step that I described earlier on. And in some situations, you can decide that either the QC or the OQC is redundant, so maybe you just want to do the kind of functional testing at the end rather than after you first put down the enzyme. But this can be, how would I put it? This can be optimized or streamlined, because as you start to produce materials and you start to see what your yields are like and where your pain points are, you can kind of optimize where you should be doing your kind of how do I put it? Where you should be doing your quality control steps, for example. And again, Julie is an online database that we have. People can buy a subscription to it. If they're working with us, it's quite useful because we can put data there, they can put data there, we can analyze data, they can analyze data. So it really helps with that kind of working with ZP. Just want to touch on IQC. This is incoming quality control. This is the kind of, let's say you were producing something like a glucose strip by sputtering electrodes or by screen printing electrodes. One of the first things that you could do is electrical testing. I will talk about this in a minute, but it's sort of the idea that you come in with what's called like a probe station and you check the continuity of your conducting tracks. In electrochemical biosensing, electrical testing is useful, but I will sort of make some comments about it. Profilimetry, this is something that we have used on client products and projects. I will sort of make some notes about it. Visual inspection, everyone does visual inspection. If anything, the minimum you would have expected from, let's say you were receiving screen printed electrodes from a vendor, is the minimum would be visual inspection. You often see that they will sort of cross off certain electrodes that they think are no good. Visual inspection is, yeah, it's useful, it's quick to do, but it doesn't tell the full story. And again, something that we do that's quite different is electrochemical functional testing. And I will describe that again in more detail. First of all, just about continuity or resistance sort of testing. You have maybe contact pads for your electronics, maybe you have electrodes where you're going to put things like the enzymes, and you want to know that there's good continuity between the contact pads and the electrodes. And so you can bring what's called a probes in and just test the ohmic resistance there. And you at least want it to be consistent, and you don't want it from batch to batch to be super variable. If the resistance is low, that's probably a good thing, because you're not going to distort your signal due to what's called sort of ohmic effects or resistance effects. So we would often check the continuity of that. But I do want to say that I will touch upon electrochemical testing in a minute, which is something that we do that's quite unique. We have a unique workstation for it, which we make available to collaborators. And we have the Julie system, and that will do electrochemical testing, which actually will give you essentially the electrical resistance or continuity testing for free anyway. So people do this, but actually doesn't tell them the whole story. And when the product doesn't work, then they're sort of scratching their heads. So it's easy to do, it's easy to automate. It's useful for spotting gross problems, and gross problems would be like open circuits, i.e. there's that track has got a crack in it, a break in it. Short circuits, two tracks that shouldn't necessarily be touching are touching because some conductive materials come between them. That would be a short circuit. Gross resistance problems for whatever reason. We've seen this happen as well, where a vendor has, for example, diluted the carbon ink to make it more printable, and suddenly the resistance shoots right up, so you can sort of spot those kind of problems. But it has, I say here, limited surface characterization, practically no surface characterization. There's a very important surface in these kind of electrochemical sensors, and that surface is that kind of working electrode where you're going to put your enzyme, for example, and the solution that, for example, the blood or the saliva, there's a resistance at that interface, and this electrical resistance measurements gives you no indication of that interface. It's really important, and it's not addressed by this sort of testing. Profilimetry, we have used it on client projects just to get a sense of the print thickness. It's not really a near line test that you can implement in day out testing. It's useful for characterization, during a development phase, but I'll make some comments about it now. It's easy to do, great. It's useful for spotting sort of gross errors. True. Problem is with it, you can't test that many sort of, let's say, samples. So to get a statistically useful number could be quite time consuming. Limited surface characterization. What I mean by that is it will tell you the sort of roughness of the surface, etc., and that is useful, but it's still not telling me this electrochemical resistance at the electrode that I'm really kind of interested in. it's useful but not necessarily critical. Visual inspection, everyone does visual inspection. Um, so at Zimmer and Peacock, we have a system called Julie, which means that it's a cloud database, but we can bring images of, let's say, a sheet of electrodes, um, pass it through the Julie algorithms, and we can spot, and it's not very hard to spot those paw prints there, for example. So visual inspection, easy to do, easy to automate. Again, limited surface characterization, but everyone does it. Something that not everyone does, but we definitely do, is electrochemical functional testing. Um, so we have a unique parallel test station that we use in our manufacturing and we make available to others, and it works with our cloud database system called Julie, and it allows us, one unit will test 6 electrodes. We often use 2 units in parallel, and we're testing essentially 12 electrodes. Now it allows us to use a whole plethora of electrochemical techniques, and the one that we would actually use now, it means that we have to bring essentially liquid test solution to these electrodes, and then we can use an electrochemical technique. Here I'm showing sort of cyclovoltammetry. Cyclovoltammetry is nice because it's fairly quick, it's fairly easy to program, and it gives us a good sense of the electrodes, how the electrode's behaving. We would, I want to say, adapt it, because what the reason I would say that is because you really don't want to be testing with a technique that's not representative of how you're functionally going to use that sensor. So you've got to be a little bit careful, but a starting point would be, for us, we would start with potentially cyclovoltammetry, but I would be cautious. Like, for example, if your electrode is going to be used what we call like a poise potential of 50 millivolts, you wouldn't be testing it out at 950 millivolts, because that's nowhere near where you'd be using that electrode. But we would take those kind of things into account. Now, when we do this kind of work, it's more like a sort of consulting and program phase, because people look to us and say, oh, well, just do it as routine testing. No, there's a break in time that we have to be involved with a bit more of the cerebral matter. Anyway, that said, I've said so far, that we can do electrical or continuity testing, sure, but you actually get it for free when you do this kind of testing anyway. Profilimetry, sure, it's useful, but it's not going to be a day in, day out sort of QC tool necessarily for you. And then you can, visual inspection, I think, is, you might as well do it, to be honest with you, because you will spot all the gross things pretty quickly. When I say gross errors, I should say. And then there's this last one that we do at ZP that's a little bit more unique, because actually we've got these parallel test stations. They can run anything that we could have otherwise done in our labs. We can then run it in the manufacturing arena. We put test solutions on those electrodes, and then we can start characterizing those solutions. And importantly, it tells us something about the interface between the electrode and the solution. And that's, none of the other tests that I've so far listed actually tell you about that. So this is cyclovoltammetry. This is the cyclovoltammetry of ferricyanide. And what we're looking for when we're doing this, when we're characterizing electrodes, for example, doing manufacturing, we're looking at the peak position. I should actually say the peak height first of all. So the peak height, because the peak height is really telling us something about the electrode area, the electrode roughness, the conductivity of those electrical tracks that I was talking about earlier on, and it's also telling us something about the electrical resistance between the electrode and liquid. And as I say, none of the other tests actually did that. So we're very interested in peak height. We're also interested in peak position. If these peaks start separating from one another, it's again telling us something about, is that carbon ink that I'm using, that I'm printing, is it low resistance or high resistance? If it's high resistance, these peaks start separating from each other. The lower the resistance, they tend to be closer to one another. So we are interested in things like peak height and peak position, and it tells us a lot of things. It tells us, and I know I've said it, the continuity of the tracks, everything is working correctly. It tells us something about the roughness of the electrode, the area of the electrode, and it tells us something about the resistance at that electrode interface. So it's a useful technique. Importantly as well, because you saw earlier on in the earlier slide that we're actually doing this in parallel. So now we're starting to also understand repeatability. And it's important that I bring up the icon for the Julie database again. Julie is really a cloud system that we've had in development, have been using now for 8 years. So it's really kind of become a sophisticated tool for us. So for example, we can do a whole lot of parallel testing. We can just upload that data straight to Julie. Julie will come in and analyze, for example, our, I think in this case, our peak height, and we can get a relative standard deviation here of 4%. So that RSD is just the standard deviation divided by the mean value. You can you can see it there, 0.134 divided by 3.597. And some people call that the coefficient of variation. So they sort of talk about CV value. Some people talk about relative standard deviation, but we're all talking the same thing. So often with us, if we're screen printed and screen printing electrodes, then we will get RSDs below 5%, 4% and 3%. These are kind of RSDs that you should be able to get when screen printing. Um, Something else that we do as well is, I did say that we were very interested in peak height and peak position. And because we've got this system called Julie, it's really quite unique, because what it allows us to do is say, okay, go and find me those peak positions, for example. So Julie can do that. Where are these two peaks essentially in this one? And actually we can set a criteria on there. There's nothing worse than having a sort of quality system that's a bit subjective. It's good to have human beings involved in things, but you really want to have a very objective measurement, and so trying to sort of take the human being slightly out of the equation helps with that. So what we can do in Julie, for example, is then set a criteria that kind of says, if the in this case, if the peak separation is less than 0.25, that means 0.25 volts or 250 millivolts, then it's a pass, and all these have actually passed. We can also do another one, which is actually look at these two heights and say, if the peak to peak difference is greater than 6 microamps, so that's what we've set here. So we're looking for, at least to have a good amount of, let's say, signal. If we get that, then we can also pass that. So here we've set the criteria on other peaks not too separated. If so, it's check, and are the peak heights above a certain threshold? If so, then pass. So you can see that we can do the testing on the parallel system. Data goes straight to Julie. You can then do set criteria in Julie, and the whole thing can actually then spit out a report as well, so that it very much minimizes the human aspect to this, which is good when you're trying to make as I say, these objective and streamlined processes. Also, the use of CV. If we see something gross, like these are sort of two CVs that I would say are sort of showing gross defects. This CV, one of the CVs on the left, is actually showing what we call a contamination of silver, and the one on the right, I don't know what it's doing, but it does not look good. At which point then, the Julie can come in there and just reject these straight out and say, there's something went wrong, and which is good, because then you won't carry these electrodes forward in your sort of manufacturing process, because obviously the later you catch these problems, the more you've invested in them, and then basically the more money you've essentially lost. Now, I have talked about Julie being super useful for telling us things like peak height, peak position, pass and fail criteria, but also when you're producing, for example, electrodes, whether it's reel to reel or by sheet, you've essentially got these rows and columns of electrodes. And what we can come in then is we can come in and actually test these rows and columns. We can set some pass-fail criteria, and we can essentially spot bad electrodes and tell you where they actually are on that sheet. And we kind of call this wafer mapping. This is used a lot in the electronics industry, at least the concept of, I've got a wafer, they call it, of semiconductor parts, and they go in there and they say, we mapped them all, and actually they're all in spec apart from a few bad ones. And that's something that we also do, but I think we're the only company to do it actually in the biosensor space. And we also can do it from sheet to sheet to sheet, so we can come in, test at the beginning of production, middle of production, and at the end of production, and essentially build up a heat map and understand how parameters, things like peak position, peak height, for example, are changing during the manufacturing as well. And then make sure everything sort of stays within spec. And if it doesn't, it gives us a way of then being able to deal with those kind of problems. So far, I've really been talking about how we would characterize or do quality control really just on the screen printed electro part. I haven't talked really about functionalization, but there's a next phase now, and we would use the same equipment, so you can kind of see that there's not a redundancy in terms of this equipment's only used once. We actually could bring the electrodes in, but now maybe they've been functionalized with an enzyme. In the case of glucose strips, that would be GDHFAD, and then we can test them, and we can do CV or we can do amperometry. The reason I mention that is because at this point we want to be doing what we would describe as functional testing in the way that the sensor was actually going to be used. So with most glucose strips today, they're really amperometric sensors, so there's a certain voltage that they're using, and there's a certain current profile that comes off that, and there's probably a what we call an AC component to it as well. And what I mean by an AC component is people may be wanting to measure the hematocrit, the amount of red blood cells. So there's a certain waveform that we would then adopt and use for testing as well. So we have the electrode. It's been functionalized in some way towards the analyte of interest, and we could be doing that either on before the microfluidics or after the microfluidics. You start to choose where to do this really based on the experience. What I mean by that is if your production line is generally yielding well, then you can wait to the end. But if you've got a problem in that deposition step of enzyme, maybe you have to go in and start sacrificing some sensors at that point. But the later you leave it in some ways, then the more representative of the final product that testing will be. So here I'm just indicating that we would, for example, test sensors that have been functionalized with enzyme, maybe at 3, for example, glucose concentrations. So maybe 45 mg per dl, 90 mg per dl, maybe 180 mg per dl, which is approximately, 180 mg per dl is about, 90 mg per dl is about 5 millimolar. So 180 mg per dl is about 10 millimolar. But what I'm saying here is test low, high, and low, medium, and high concentrations, and we would get signal versus concentration. So we've added a kind of another element to this. Again, we can put all this data through Julie, and suddenly all the kind of crunching of data, spreadsheets, etc., it really does go away. Our engineers really love it. So this is an example here where we've got we've actually tested it at more than 3 concentrations. I can see here this is not a glucose sensor, this is another type of sensor, but they've been tested at 0, 0.5, 2, and 4 millimolar. And what's happening here is then we test low, we test a little bit higher, we test higher still, test higher still, we test higher still, and that extraction of signal versus concentration, that didn't require an engineer to do that. The Julie database is actually doing that for them. And again, there's a bar along the top here, and that's actually containing kind of critical parameters, things like limit of blank, limit of detection, limit of quantification. So Julie is able to receive, crunch, and extract information, I would say, from the data, and it really saves an awful lot of time. And it's the same as before that. You don't have to just do it on a few sensors. We can do it sheet by sheet and end up characterizing the entire run and doing things like heat maps again. So I will finish with that. Say thank you very much. And if you have any questions around the contract development, the contract manufacturing, or consulting into these kind of things, then don't hesitate to contact us. And I would say that Julie and the hardware is something that we make available to clients as part of interactions with us. So if you have any questions, please reach out to us at Zimmer Peacock. Okay, thanks very much.